missing a bunch of people.
They probably thought that we were getting our test back today.
No, that's not happening. So, last time we were talking about how to tell whether or not a force is conservative. And although we didn't prove it because that is done in math methods and Calc 3 and other courses, we find that a conservative force will have its curl vanish in a particular region where it's conservative, and vice versa. If the curl of a particular force vanishes, then we can say that it must be conservative in that region. And what that means for us is that we can write it as the gradient, the negative gradient of a scalar function. Right? We're basing this on the theorem, the mathematical theorem that the curl of a gradient is always going to be 0. Okay? So let's just start off with an example for you to consider. So the question that I have for you is, I'm going to give you a force, and I'll give it, we'll just have a two-dimensional force here, only has an x and a y component. And the question is it conservative? And if so, let's find a potential energy function, assuming that at the origin, the potential energy is going to be 0. And if not, can we modify the force in some way, add another component or change one of these components in order to make it conservative. Okay, so I'd like you to work on this for a few minutes. Answer just this first question here, and then I'll check in with you and we'll see where to go from there, which of these paths we want to take. But I want you to figure this out, whether or not this force is conservative. You can work with someone else around you if you want to, and in a few minutes I'll ask you for your answer.
It is conservative because it's less 0. So there's no finding here.
You know how to do a potential function? I remember how to do that. So,
Okay, bueno.
so say we're going to go from 0, 0, 0 to, what is it, ABC?
So any 3 variables is fine.
Any command.
So use ABC.
Okay, let's try to remember this. We're going to do a line integral. Should I keep it recording? Okay.
Yeah, well, Logan can hear our pulse it down.
From
This is our physics ASMR.
0 to, x, y, z. That's what it is, x, y, z. So x not 0, 0. So I think it's we do an integral from 0 to x. So here's the dx, dy 0, dz, and dy 0. So we just did that goes off, so it'll be 6x here, y is 0, dx. So that just equals 0. So now we're going to go from x 0, 0 to x,
It's y,
y 0. So here x, that's just going to be our
Wait.
x naught,
Wait, so this is 6xy?
y, but y is 0.
I see, okay. Okay, wait, let me do this one. 0, y, and you got the 6x from there, so I would use this one here.
Oh yeah, but this has to become a dx is 0, so that goes away. This is dy, y, so 3 x naught squared plus y squared. Plus 3y squared. Yeah.
dy.
Yeah.
And so x naught is just x naught. And okay, so wouldn't that be 3x naught squared y plus y
B from 0 to y.
from 0 to y? So it would just be that, right?
Yeah. Now let's test it. Take the.
Why do we not have to do it from c because the c component is 0?
It's gonna be. I mean, we can try it from 0 to z, but the d. Okay, let's do it. Yeah, do it from 0 to z. So then we do integrated 0 to z, and but dx and dy are constant. It becomes 0, and there's no z, so it's just 0.
Oh, okay,
Is it
okay,
zero?
yeah, okay.
Okay, so let's take the gradient to this.
Oh, yay. Wait, do I need to combine it? Oh, that was 0.
Just take the gradient just to check
Okay.
our answer. So that becomes 6x y plus
Okay,
that's it, yeah.
that works.
Well,
But that's a scalar function, it's not a vector like up here. But oh wait, no way, man. I just had the screen replaced.
you gotta change this to just regular x.
Right.
3x squared y plus 3y cubed, you said, right?
Yeah.
So with respect to x, turns out that goes away, so it's just 6xy. Now with respect to y, it's just 3x squared plus, there's an error here.
We have another 30 seconds or so just to answer that first part for me.
This is just a regular y.
3 or 30?
Huh?
30. I thought you said okay.
Why?
3 seconds.
Oh yeah, it is regular.
Oh wait, yeah, it is right.
Yeah. So the answer is just that. So the answer is just 3x squared y plus, plus y cubed. Is our potential function. We'll define it like this.
Assuming u equals 0. Okay, and at 0, 0, that's 0. And if not, can we mod? Well, it is conservative, so that doesn't matter.
Many elbow as these both helping.
That's the Mahler-Navarro way.
Okay. So, yes or no, is it conservative?
C.
Yes?
Yeah.
All right, so you computed the curl and all 3 components vanished? I'll trust you. Okay. Did anyone work on the second part?
We did.
You made some progress? Okay, so how did you approach the second part? If we want to know, okay, it's conservative, so we want to find the potential energy function. I suppose I should write this as u of x, y, and z, although there's no z component for a force, so the z information is pretty boring. We'll keep that in there. How did you approach that?
So it seems that we did a path integral from 0, 0, 0 to x naught, y naught 0, and the path we took was from
Okay.
0, 0, 0 to 0, x naught 0, to x naught 0, 0, and then from x naught 0, 0 to x naught, y naught 0.
Okay, so path integral from 0, 0, 0 to like x, y, z, but like passing through, like doing first in the x direction, then in the y direction, and then in the z direction?
Yeah.
Yeah.
Okay, so 0, 0, 0 to like x, 0, 0 to like x, y, 0, and then to like x, y, and z. I like it. That's totally not how I did it. Oh, well, except it kind of is, but I was just thinking about it very slightly differently. Yeah.
I think notationally, because it's, a vector, it kind of gets garbled up. I literally just did the integral of that function with respect to I split it up into like 2 different things.
Okay.
I did like the integral with respect to x of the 6xy,
Okay.
and then I just added that result with the integral with respect to y of those 3.
Okay, so you were using the fact that the partial derivative of the potential energy function with respect to x with a minus sign, right, is supposed to equal 6xy.
Right.
Right, and partial derivative with respect to y and a minus sign is supposed to equal 3 times x squared plus y squared. And if we want to put it in, the potential energy function derivative with respect to z is a big fat 0.
Yeah.
Right? And then saying, well, let's just integrate this thing with respect to x and integrate this thing with respect to y and see what we get. And then like add the results together.
Yeah.
Okay. So we run into a little bit of danger if we just add them together. Okay? Because, well, let's just do that. Okay? So let's integrate this, right? This will say that u, as a function of x, y, and z, is going to be the integral of negative 6xy with respect to x. Right? At least for this stage, this is equivalent to doing the first step in the path integral. Right? Because we're just taking, if we're in the x direction, we're only looking at the x component of the force. Right? This is the integral of fx dx, and then we're going to put a minus sign on it in order to get the change in potential energy. Right? And we're integrating from 0 to some arbitrary x. Okay, so we do that. The 6 and the y we can pull out, right? And the x dx is going to give us an x squared over 2, so this gives us a negative 3x squared y. Is that right? Okay. I didn't put limits on my integration. So what am I going to have to do? Plus a constant. Here's where we have to be really careful. Okay, well, I'll put it in as a constant, and then we're going to come back and actually change this in a bit. But let's do this integral as well and see what happens. Okay, if we integrate u sub y, or du dy, so we've got negative 3 times x squared plus y squared. We're going to integrate that with respect to y. Okay, what do we end up getting from this integral?
Negative 3x squared y.
Okay, negative 3x squared y
Minus y cubed.
minus a y cubed. Okay? Plus a constant.
Plus c, yes.
Right? Plus a different constant, perhaps, right? So let's call it d instead of c. Cx and cy, I don't care how we compute this. But now here's the issue. If we just take this expression and this expression and add them together, we've got this negative 3x squared y that's in common to both of them. And we're basically overcounting that. Okay? So we can't just say, let's get this expression, integrate it, and then add them, because now it's like we've got 2 potential energy functions that we put together. Does that make sense? In other words, integrating with respect to x over here and integrating with respect to y over here, they're actually connected to each other. We know that if we were to do a path integral, we would go first in the x direction, then in the y direction, then in the z direction, and frankly, the order doesn't matter. But if we're integrating here with respect to x, I'm going to actually erase this for the time being. We'll come back to this, this portion. This constant is a constant with respect to x. It doesn't depend on x, because we integrated with respect to x. But it could depend on y or z. So this constant isn't actually just a number. This constant is really some sort of function, let's call it little f, that depends on y and z but not x. Because we only integrated with respect to x here. And we know that our expression, our final answer, could depend on x, y, and z. So we're getting our x dependence here, but our y and z dependence is here, and we also have y dependence here. Okay, so by doing this, we're allowing for the fact that we could have some functional form that has y dependence beyond what we've had here, and have z dependence. Because, remember, this is the result of doing this integral is supposed to be our potential energy function. It's supposed to be everything. And we don't know what this function is yet, but this expression should be, once we figure out what this function f is, should be complete. Okay? So what we can do is we can take this expression, and once we have it, we can figure out what f is going to be, because we can say, okay, now let's bring in the fact that the partial derivative of our potential energy function with respect to y is equal to this term. Right? So if we say negative du dy of this expression, we're now going to get this first term, which is a 3x squared, right? Take the derivative with respect to y, plop a minus sign on it. And then we've got this expression where, well, we don't know what this derivative is yet, but we can just write it as the partial derivative of f with respect to y. And now we say this thing has to equal 3 times x squared plus y squared. Now, our 3x squared term here and here match up. And what's left over is something that tells us how our function of y and z depends on y and z. Well, we've got this 3 times y squared expression. Okay? So now we can integrate this. We're not integrating the entire potential energy expression. We're just integrating what was left over after we did the x integral. We can integrate that with respect to y. And so we get something that says f of y and z is the integral of negative 3y squared dy. And so we said that that's going to equal this y cubed, again with a minus sign here, plus a constant, but our constant can still depend on z, right? Because we now integrated with respect to x. We had a function that depends on y and z. Now we're integrating that y-z dependent function as something that's integrated with respect to y. But we could still have some z dependence left over. So we've got some function g of z that's left over. And now we have to figure out what that is. Well, that actually turns out to be pretty easy because our force didn't have any z dependence in it. So that g of z function is just going to be some sort of constant, right? But, you know, at this point, what we have is that our potential energy function looks like negative 3x squared y minus a y cubed plus this function g of z, right? We've gotten this first term from doing the first integral. We've gotten the second term from combining that information with the second integral. Now we have that leftover function of z. And then we can say, oh wait, well, du dz is equal to 0. And so that tells us that the derivative of g with respect to z, which we can just write as an ordinary derivative, since it's derivative of one variable, is 0, which tells us g of z really is a constant. Right? And so our potential energy expression now looks like negative 3x squared y minus a y cubed plus a big fat constant. And how do we figure out what this constant is supposed to be?
U 0 at the origin.
Yeah. And then since u has to be 0 at the origin, the value of this constant actually ends up being 0 in order to make that work out. Okay, so this approach is, frankly, it is exactly the same result as the path integral approach. If we wanted to sort of, do this path integral approach, we could. Right? We integrate the x component with respect to x, and again we would get a 3x squared y, evaluated at the endpoints of x equals 0 and x equals some sort of x final. So we should call this x prime like that, with a minus sign. Okay, and then. So there's our result from integrating along the path 0, 0, 0 to x 0, 0. then we would say, let's integrate along the path from x00 to xy0. So now we're going to integrate the y component, right, with respect to y. And we've got to say, well, we're starting off at a y equals 0 and the final y of y. But with this x value put in for what we have in our expression. And let's see, so our function now was 3 x squared plus y squared, all right, integrated with respect to y, I guess y prime.
Wouldn't it be 3x squared plus 3y
Oh,
squared?
yes, I'm sorry, yes, this 3 is actually outside. All right, so half integral from this first portion, half integral from the second portion. So now we're going to get a negative 3 x squared y. Well, let's see here.
The first integral
Wouldn't the
should
first
be
step be 0?
zero,
Because the y isn't changing along that path. It just stays at 0.
Say it again, sorry.
Shouldn't the path integral from 0, 0, 0 to x 0, 0 be 0 because your y stays 0? There's no change in y.
Yes, thank you. Yes. This first term, yes, yes, yes. Y equals 0. There we go. Yeah. I was worried we were going to get an extra term here. But you're right. Y equals 0 along this path, but x is not equal to 0 along this path, right? And so we're going to get this negative 3x squared y minus a y cubed, right? Primes there. Evaluate from y prime equals 0 up to y prime equals some sort of y final. All right. And then we got to integrate the minus sign, the z component of our force dz, but there's no z component, so that vanishes. So in the end, there's our answer. Which, yeah.
Yeah, I was gonna ask, that's whenever I just originally added the integrals, that's about what I got.
Okay.
So I'm just curious, like, will there be instances where that isn't the correct way?
No, either method will give us the correct idea, right? We either do this explicit path integral and say, well, our path isn't supposed to matter, so let's just pick the simplest possible path, go and zip, and then zip, right? I mean, I suppose we could have done along some sort of straight line, but that's more complicated, right? So we go first in the x direction, then in the y direction, then in the z direction if necessary. Or we can do this approach by saying, we know what the partial derivatives of our potential energy are supposed to be. We've got 3 partial derivatives. We need to make them match up. Okay? And if you're more careful than I was when originally doing this path integral method, then either answer should be the one that we're looking for. But what we can't do is just integrate this thing here by itself, and then just integrate this thing here by itself, and then add them together without being more careful about having particular values, right? If I just integrate this thing, negative 3x squared y, but I don't use the fact that, well, really, this has got to be true for arbitrary paths, and I'm choosing a particular path where y equals 0, right? Then we end up getting the doubling that we had here. Which method do you feel is easier for you? The path integral method or the mixing and matching derivatives method?
Path
Like the
integral.
path
integral, it's the same, it's just
Okay.
straightforward.
Path.
I always learned it this way.
That's how they taught it to us at first, but then
Cooley.
I think Cooley did the path integral,
Yeah.
path integral version.
Yeah. Yeah, it has a lot to recommend. But I wanted to make sure to show that method because I think that's what you learn first, right? At least that's what I learned first. I think there are probably some cases in which the second method is easier than the path integral method. And it probably depends on just the details of the form of the function. Right? You can also decide you're going to choose a different type of path. But again, for us, the sort of straight line segment paths probably makes the most sense, because then we're doing a series of single integrals with independent variables. All right. So the next thing that we're going to talk about is the idea of looking at potential energy functions and trying to get information from the graph of the function. And so, in general, this is going to be some sort of surface graph. It's going to be something that depends on x, y, and z, or maybe just x and y, or maybe just x. For our purposes, to start off, let's just look at the 1D case for now. Okay, and the concepts that we're developing will mostly carry over to 2D or 3D situations. So, all right, let's say we have a situation where only conservative forces act on an object that is undergoing 1D motion. Okay? So what that means is that we've got some potential energy function, which we could write as the negative integral of those forces with respect to x, or we could write this as our forces are an ordinary derivative of u with respect to x, and an overall minus sign. And because we have only conservative forces acting on our object in 1D, we can say that the total mechanical energy is conserved. So kinetic energy plus potential energy is going to equal total mechanical energy, which is some sort of constant value. Okay, again, in 1D, we can write this. In 2 or 3D, well, we'd have to have a function of x, y, and z, and we'd have to maybe write out our kinetic energy term with maybe a little bit more detail. I mean, this is still just the kinetic energy of one part, but we might want to break that up into contributions from motion in x and y and z. It's not a vector component, but we can think about it as being contributions from different forms of kinetic energy. In one dimension, this is actually a differential equation that is separable. Because velocity is just a time derivative of position, right? So we could write this as 1/2 m, and since we're only in one dimension, our velocity is really just x dot. So 1/2 m times x dot squared. And let's move the potential energy over to the other side of the equation. So E minus potential energy equals kinetic energy. And let's multiply both sides by 2 and divide by m. So we get x dot squared is equal to 2 over m times E minus our potential energy. And really x dot is just, if you want to write that out in more detail, that's dx dt squared. So if I want to solve this differential equation, what should I do next?
Take the square root of both sides.
Say that again?
Take the square root of both sides.
Okay, take the square root of both sides. So dx dt is equal to the square root of 2 over m times e minus u of x. Hang on a sec, I made a mistake. There we go. Plus or minus, right? We don't know whether the velocity is positive or negative. Could be both, depending on what type of motion we have.
Does it matter?
Well, it does matter, because, I mean, we're going to get different answers if we have an object moving to the right or to the left. So we have to allow for both possibilities, right? And then, yeah, we can move the x-dependent stuff over to the left-hand side and move the t over to the right-hand side. So we get dx over the square root of 2 over m times E minus potential energy, and let's put plus or minus along with it. It's just equal to dt. Right, and so slap an integral sign on both sides. And we could write this as something like, well, the integral plus or minus from some like x initial to some x final of dx over the square root of 2 over m times e minus u of x is equal to integrating the other side is just going to give us t final minus t initial. So, what this tells us is that, in principle, if we know the potential energy function, then it's possible to plug this in to the integral, do this integral, maybe even do this integral analytically instead of having to do it numerically. And what we then find is basically t as a function of x, right? T final depends on something involving x final. And then hopefully we can invert that to find a trajectory, right? X as a function of time instead of time as a function of x. And the problem is, this is generally speaking a hard integral to do analytically, right? We can feed it to a computer and have the computer do it numerically, or put it into Wolfram Alpha and hope Wolfram Alpha gives us something that makes sense. But there are only a few potential energy functions that we can put in there and actually get a decent looking analytical result. So that may be a problem of this method, but it turns out that even without going through this integration process, there's a lot of qualitative information that we can get out of looking at the potential energy graph. Okay, so let's draw an example of potential energy graph. And again, in just one dimension here for the time being. Let's see. No, let's see. Yeah, something like that. Extend my axes out a bit here. Tell me where there might be some interesting locations on this graph.
Maximum minimums.
Okay, so troughs and peaks. So let's say that we've got a peak here. Let's call that x1. Then we've got a trough here. We'll call that x2. Another peak x3. Another trough x4. And finally, a peak x5. So since this is a graph of potential energy, it can often be useful to look at the difference between the potential energy and the total energy, right? Total mechanical energy. That's what shows up in this integral. So on this graph, we would draw a horizontal line to represent the total energy, the total mechanical energy for this system. And then just the height of that line tells us the value of that total mechanical energy. And the location of that energy is then going to tell us what kind of motion we can have, what types of motion are allowed. Before we get into that, let's just remind ourselves that, so you said that the peaks and troughs were interesting. What's so special about the peaks and troughs?
Derivative equals 0.
Okay, derivative equals 0. So the derivative of the potential energy function is force, negative of the force, right? So since the force is negative du dx, right, this tells us that the locations where the slope vanishes, right, are equivalent to locations where the acceleration is 0, and acceleration equals 0 is just another way of saying that these are finding equilibrium locations. So that means if we choose one of these locations and we place our object there at rest, it's going to stay there, because it's not initially moving from that place, and there's no force that's going to change its motion. All right, so I can place an object here, or right there, or there, or there, any one of these 5 locations, and if it has no initial velocity, it's just going to stay there forever. What happens if I don't place the object exactly on one of those locations? Let's say instead I place the object slightly displaced from one of these troughs.
Towards the trough.
It will probably move towards the trough. So even if I let it go from rest. Okay? Well, so if I place the object right here, what sort of force does it experience?
Minimal.
Minimal, but non-zero.
Yeah.
Right? Which direction?
Towards the drop.
Okay, yeah, because the derivative tells us the slope of, the slope of the graph, right, the derivative, with a minus sign tells us how much force we have. So over here we have a positive slope, which means we have a force pointing in the negative x direction, right? And over here,
Opposite.
okay, points to the right. So here we have an example of what we would call a stable equilibrium location. It's stable because if we start slightly away from it, the force associated with this potential energy is going to draw us towards that location. And if we start here from rest, the force draws us here, we maybe overshoot because we build up some speed, we go over here to the other side, and then we get drawn back again. Right, so we'll oscillate back and forth. What happens if I look at one of these peaks and I displace the particle very slightly away from one of those peaks?
Should go away.
Okay, it goes away, right, because here we have a negative slope, which means that we have a force with a positive x component. So that force is going to be drawing us further away from that critical point. And same idea over on the other side. Right? So this would be an example of what we call an unstable equilibrium. Right? We've got stable points here. And I guess here. And we've got unstable points there. There, and there. Okay. Well, what we don't actually have on this graph, we don't have an example of it. What happens if I have a critical point that's like that? Right? Here I have a location where the slope is 0. Well, I mean, yeah, it's kind of like a saddle, although in one dimension we don't really have saddle points, right? But we can talk about that in 2 or 3 dimensions. If I displace the particle slightly to this side, what happens?
It'll go down and keep going.
Okay, it goes down back towards this equilibrium point, but it's probably going to build up some speed and overshoot, right? And if I displace the particle over here, what happens? Okay, it gets drawn further away. Right, so this is an example of a location that doesn't seem to have stable behavior, right? Although, well, yes, and this is generally true in one dimension, right? Since we can't have saddles, a saddle point, as we'll see in more than one dimension, is where we have something that looks like a trough in one dimension, but a peak in another dimension. Like a better example than a saddle is a Pringles chip, right? Should have brought Pringles. But in 1D, this is still going to eventually be unstable, right? Because no matter which way we displace our object from that equilibrium, from that inflection point, we could eventually leave that equilibrium location. Okay. One other thing to think about is, like I said, drawing an energy line, a total energy line on this graph is something that's going to be useful, right? What happens if I have an object that is placed right here? So this is the total mechanical energy, right? I place the object there, and I let it go. And I'm letting it go from rest. How do I know from this graph that I'm letting this object go from rest?
Because the potential and kinetic equation.
Because the potential and...
Oh, the potential is at the total energy, so...
Right. So E minus potential is equal to 0, right? So our kinetic energy is equal to 0 if I place the object there, right? So I know I'm releasing from rest. If I were to place the object here, and I knew that this was the value of my total energy, then I would know that the object actually has some initial velocity, right? What I don't know is if I have the object here and my total energy is up here, I actually don't know whether the velocity is to the left or to the right, because plus or minus, right? It could be either. So if I just tell you the object starts here and my total energy is here, what I haven't told you yet is whether it's moving to the left or right. But the fact that the value of that total mechanical energy tells us something about the motion of the particle, the speed that it has in a particular spot, means that in addition to knowing these locations for equilibrium points, having certain critical values of energy are going to tell us something different about the motion.
So
Yeah.
should your potential energy function not cross the total energy line?
Oh, it certainly can. I can still draw the potential energy function up this high, right? Does my particle ever get there? No, I can't have a particle up here because that would have a negative amount of kinetic energy, which we're not allowed to have. Right? We're only allowed to have non-negative kinetic energy. So this region would then represent a region that is not accessible to our particle. It's a forbidden region for this value of energy. But if I raise the energy value, then all of a sudden that region becomes accessible. So what would be some values of energy that we think would be important in distinguishing the types of motion that we have? Where should I place some horizontal lines here that could sort of divide up this graph into different types of motion?
In regards to the one at E.
Well, there's nothing special about that line, is there? Okay, could have a line that's at the peaks, at any of the peaks. Okay, so I really have 3 locations there, right? That peak, or that one. So, all right, let's do that. I'm going to run out of colors, but let's draw an energy up there. Let's draw an energy for this next.
That only matters that peak?
Hmm?
Well, it's not important towards the initial, because it crosses the U exit point.
Oh, it's still important.
Okay.
Yeah. And if it's not, we can erase it later. And then you said I need another one. Let's use, where's my green? This is my green. There it is. Okay. I've got another peak here. There. Okay. What other levels of energy might be important?
The troughs.
Yeah, maybe where the troughs are, right? So I've got a trough here, and I've got finally a trough down here. Okay, so the 1, 2, 3, 4, 5 is not going to match the labeling for this. I'm just going to also label these as E1, 2, 3, 4, and 5, and we'll deal with it. So this is energy, call it energy 1, this is energy 2, energy 3, energy 4, and energy 5. And let's classify the motion according to what happens for values of total mechanical energy that are in between these sort of what seem like critical values. Right? So if E is less than energy 1, what happens? My energy is actually like down here.
Get lower than that.
Yeah, I can't actually do that, right? My particle doesn't have a way to exist if my energy is below the lowest value of energy that's on the graph, right? So this is just not allowed, right? Because this energy value is less than our potential energy everywhere. Okay, so that's not a particularly interesting motion. What if the energy is in between E1 and E2? What can we say about the particle's motion?
Confined to the part of the function between those two
Okay.
lines.
So, okay, let's call this like region 1, so we got another one of those over here. Let's call this region 2. So we would say that the particle is only allowed in region 2?
Yes.
And what type of motion does it have? Has some sort of oscillating motion back and forth, right? It's going to slosh around. Call it periodic motion, but it's going to go back and forth inside that potential energy region. Okay, what about for E2 less than E less than E3? Energy is in between 2 and 3. What can happen?
It's going to be confined to region 1.
Okay.
So
So only region 1?
and the area above region 2, but not all of it? Oh, yeah.
So it's allowed in this region over here.
Yes.
Okay. Is it allowed over here?
I mean, I guess so,
Yeah.
but there's parts of it can't access. So that's
Well,
kinda-
sure, but that was true over here too.
Yeah.
Right? It couldn't access any. If I had an energy value that was, here, then I can only access this region, that part of region 2. Right? So, same idea, right? We have a particular value of energy, say here, like halfway between E2 and E3, and we've got a region of a portion of region 1 or a portion of region 2 that our particle could be in. Could it be in both at the same time? Or like, could it be in one and then the other?
It could go over. Well,
Can it? If my energy level is here, can it go over?
yeah, because it's tangent, no?
If my energy is here, can my particle ever be here?
No.
No. Can it ever be here?
No.
No. All right, because it has to have a non-negative amount of kinetic energy. All right, so we can say that the particle is in region 1 or region 2, but it can't be both. Right? It can't go back and forth between region 1 and region 2 because it doesn't have enough energy. If my level is here, it doesn't have enough energy to get over that bulk.
What if it's exactly the top?
Oh, well, if it's exactly at E3,
Yeah, can it go over or no?
Well, it's still
That's what I was
touching a
thinking about.
point, isn't it?
well, see, the problem is, right, if it's exactly at E3,
Or just go there and stop.
then it's going to go there and stop, right? And this is an unstable equilibrium point, so all we have to do is just breathe on it the wrong way, and we send it over.
That doesn't count.
Doesn't count, right? We're not allowed to do that,
Not good enough.
okay? And frankly,
You can't breathe on them.
this is an unstable equilibrium point, but it would, for most functions, it would take arbitrarily long to get there. Okay. And in region 1 and in region 2, we can still say it's like oscillatory motion, right? Periodic motion.
In region 2, wouldn't it be accelerating towards 2? But you can't be on both sides.
If we're in region 2,
Yeah,
so if we're here and we let it go from rest,
it's gonna go down, it's gonna accelerate towards 2.
it's going to go, yeah, into region 2, right? This entire region here we can call region 2. And it gets over to this side, turns
Is that
around.
oscillating if you're missing the middle part?
We're not missing the middle part, it's still there,
Right.
right? Everything's there. Just the fact that this E2 line is here, all that's doing is setting a lower bound for the values of energy that we're talking about.
Okay.
We still have enough energy to access anywhere in this region.
I'm saying if it's exactly at E3, you want to be oscillatory.
If it's exactly at E2,
Is that?
this one,
No, E3.
if it's exactly at E3,
Because like you said, even
well, if
it's
we
over
start
there.
here,
Yeah.
yeah,
Wow.
if we start here, then it's an unstable equilibrium point and we aren't necessarily going anywhere.
If you start on the other side, is it not, will it not reach the other side or stop?
Well, if you start here, yeah, I suppose that's true. If we start here, and we release it from rest, there's nothing that says for a particular value of energy that we have to start at where it crosses. But if we do, it'll slide down here, it'll oscillate up to this point, and then, yeah, it probably won't come back. Or it'll come back only after an infinite amount of time. So, yeah, if we're at E3 or at E2, then we have this sort of crossover behavior, right? But as long as we're slightly less than E3, we're fine, right? Then we'll get to a point where it'll actually turn over and come back. What if we have a value of energy in between E3 and E4?
I'm going to oscillate through the entire thing and
Okay.
never.
So if I have a value of energy that's equal to, say, this amount,
Yeah.
it'll oscillate in regions 1 and 2?
1 and 2. Yeah.
And it can access both regions 1 and 2. Right? Okay. So we would say that particle can move among regions 1 and 2. And it still has periodic motion?
Yep.
Yeah, sure. We're here, it can slide down up to this point, turn around, come back, right? It'll have larger speed here, and certainly larger speed here, and a smaller speed here. But it'll have a value of speed pretty much everywhere. So we get periodic motion. Okay, what if at a value of energy that is in between E4 and E5?
Gone forever.
Do you agree with that?
Well, not
Oh,
off
we
to the
don't
right
know it.
side, but not the left side.
Okay, so on the left side, let's say that it's initially headed this direction.
I think you'd still go there and then come back and leave.
Okay, so it'll come here, it'll turn around,
Yeah.
and then it'll come over to this point and keep going. Because it has enough energy to get over that bump. Right? And we're assuming.
Unless you're on the other side of the hump.
Well, right, I suppose what happens if we're over here? We don't know enough about the graph to know what happens over there, right? There be dragons. But at least for here, we can say that this object is going to go off to infinity, right? And a particle that is initially heading toward the origin is going to turn around, right? Stop at a turning point, and it's going to head out to x equals infinity. So this is an example of motion that we call scattering. Because we could imagine that this particle may have started really far away and came in from infinity, right, towards the origin, gets repelled eventually, doesn't make it to the origin, and then goes back out to infinity. All the other examples of motion so far were periodic or bounded motion. This is our first example of unbound motion. But it's a particular example where it's unbound on one side, but it is bounded on the other side, at least as far as we know. And then what happens if we have a value of energy that is above E5? No, it is certainly possible. I have a value of energy that's all the way up here. That's no problem, right? I could start a particle here and it just says, oh yeah, this particle has some initial kinetic energy.
In the region we've described, it just couldn't come to rest.
Okay, it's not going to come to a stop if I have an energy that's high enough, right? It'll never come to rest anywhere on this graph. But it can still move, right? Does it ever turn around?
No, can't turn around.
Can't turn around, right? There's no turning points. If it's headed this direction, it'll keep heading that direction forever. Sometimes faster, sometimes slower, but forever. Same thing, it's headed this way. Sometimes it's going super fast, sometimes it's going slower, but it's never going to turn around. And only when the total mechanical energy level intersects our potential energy graph, that's where we can have those turning points. Questions about that? Okay, so all of this, all of what we did here was just based on understanding that the slope of the graph was related to the force, the negative slope of the graph was related to the force, and realizing that regions where the potential energy graph went above the value of our total mechanical energy were not allowed. But anywhere below that total mechanical energy level was potentially accessible. Now, I think I might have caught, when we were talking about energy levels between here and here, I think I might have caught our chemist smirking a little bit.
A little.
Why?
Huh? Quantum?
Yeah, so in quantum physics, we can get tunneling behavior. We can get a situation where in this band of energy levels, even though classically we might be confined to this region or this region, quantum mechanically there is some small probability for the particle to start out in one of these regions and tunnel through this barrier and end up in the other region. And we don't have to worry about that in this course. In 4701, 4702, that's the sort of thing that you do tackle.
We're talking about it in modern physics.
Oh, okay, good, yeah. So same basic idea. I guess did you do any calculations about that in modern physics, or just kind of qualitatively?
Just told us about it. I don't even know.
Okay. He's fair.
He didn't even grade your final exam.
He didn't even grade my final exam.
What?
Yeah, he didn't grade.
It's like good enough.
I have no idea what he gave me an A and just called it an A again.
Okay. Lucky you.
I guess so. I would have liked some feedback.
let's talk about potential energy and motion in higher dimensions. Okay, so in many ways the motion is a lot more complicated, right? But we can still say that the force is the negative gradient of the potential energy function, right? And so that tells us that the acceleration that the particle experiences is proportional to the negative gradient. Larger slopes on our potential energy surface are going to give us larger accelerations, larger net forces. And we can still say that there are equilibrium locations where the gradient vanishes, right? Because equilibrium means there's no net force. And if those equilibrium points are minima, at least local minima, then those are going to be regions of stable equilibrium. Just like we had before, if they're local maxima, then they're going to be locations where we have unstable equilibrium points. And if they're neither, right, this is what we mean by the saddle point configuration, then sometimes we call that semi-stable equilibrium. And as I said, it could be because it's stable with respect to motion in one direction, but then it's unstable with respect to motion in another direction. And also, in arbitrarily many dimensions, we can identify locations on our graph where the particle will turn around. And that's just going to be, frankly, any location where the potential energy function equals the value of the total mechanical energy. Right? So we call those equipotential surfaces, surfaces of constant potential energy. Or in a math context, sometimes you refer to these as level sets. Right? So as an example of this,
Now I have to
all right, I've got this potential energy surface here. Might be a little bit hard to see. The way that the surface is graphed is that the bluer areas are going to represent lower values of potential energy, and the yellower areas are going to represent values of higher potential energy. Okay, so do we have locations on this graph that represent stable equilibrium points?
There's a semi-stable in
Okay, so I didn't ask that. I'll ask that next. Stable equilibrium points?
Yeah.
Where? Okay, so we got two stable equilibrium points here at the centers of these blue ovals, right? Where we expect the potential energy graph bottoms out. And then you said we have a semi-stable point here. How do you know?
Because it's stable. So it's a maximum in the x direction, I guess, and a minimum in the y direction.
Okay, so if we sort of plot along an x-ish direction, we have what looks like a local maximum, right? But if we're looking in the y-ish direction, this is actually a local minimum, because we get increasing values of potential energy if we go off sort of up or down, right? So we definitely have this sort of saddle configuration in these two different directions. So we have a semi-stable equilibrium point here. Do you have any locations here that are unstable equilibrium?
Maybe at the bottom left, but you can't really tell if it's going up higher or not.
How would we how would we identify any locations of unstable equilibrium? What would they look like?
In the lower point on one side and the higher point.
I mean, it would kind of look like the blue, but if you switch the
Right.
colors.
Okay, so if we had kind of oval shapes, but they were yellowish instead of bluish, so they would indicate local peaks instead of local valleys, right? And then, yeah, I don't think we have anything on here. Maybe there's supposed to be one down here, but we don't have enough information to really tell from what we graphed. I actually think the way that I define this function there isn't one, but I don't know that for sure. Okay, so where is the force that's acting on the particle the largest, you think? Or large compared to where other places might be? Where might this thing be experiencing really large forces?
What's steepest?
Okay, how can I tell on this graph where?
So like the
the
right,
lines are-
bottom right and top left.
Okay, so like this region here and this region here?
Yeah, where the lines are close together.
Yeah, where our contours here are really close together, that means we have a steep slope there, right? And
like a
the
topography
direction
map.
of the force is going to be in the direction that's perpendicular to these surfaces, right? These level sets. So it would have a force that's pointing downward, right, into this valley here, and it's going to be a larger value of force here than it is, say, over here. So what you never want to do when you're drawing this, and this is a very common mistake to make, is if you're going to draw the force on this graph at particular locations, you never want to just draw the force as being like from one of these level sets to another one. Because that would seem to suggest that if they're further apart, you draw a larger vector, and that's actually the opposite, right? The further apart these are, the smaller the vector you draw. So in that sense, the gradient is sort of inversely proportional to the spacing between these. And in fancy physics terms, we say that the gradient is actually not a regular vector. We call it a covariant vector. We call regular vectors contravariant vectors. But again, we don't have to worry about that. We've already talked about the fact that we've got pseudo vectors. And in addition, we've got this covariant, contravariant nonsense. In a GR course, we would worry about that an awful lot, but we don't have to worry about it in this course. Unless you want to.
I got 7 minutes.
No, we got other things to get done in 7 minutes. All right, so that's just a brief example here of what you do in more than one dimension. There are a lot of times when the particle is moving in 2 or 3 dimensions, but is constrained to move along some sort of path that it can effectively be parameterized as a one-dimensional path. Okay, so we want to talk about briefly here the idea of curvilinear motion. Effectively in 1D. Okay? So this is an idea where the system itself is more than one dimension, but particle motion is constrained. To move along some sort of path that can be parameterized by a single variable. So, some examples. If we have a pendulum, right? A pendulum is going to swing back and forth, or we even had a conical pendulum, right, that was kind of rotating around in the XY plane. It would swing in like the YZ plane. But its motion is effectively one-dimensional, right? We could parameterize it just by the angle that it makes. Or we can talk about a bead on a wire. We can talk about roller coasters on a track, except if the roller coaster fails and then you don't have this curvilinear motion 1D anymore, it falls off the track. But essentially something like that. All of these are situations where we're going to have forces that constrain the particle to move along the track, constraint forces. But these constraint forces, which in general, constraint forces are not conservative, right? They're not gravity, they're not electric forces, they're not spring forces, they're like normal forces or friction forces sometimes. But constraint forces do absolutely no work on the particle because they're always normal to the particle's motion. And so that means that those constraint forces, we don't have to worry about when we're thinking about whether or not energy is conserved in the problem. Right? If I have a normal force along the track, it's not going to do work, so I can still just worry about gravity as being the only force that might be conservative in nature. Right? Let's represent the location of the particle's motion along the track by a variable that we'll just call S. Could be like the arc length along the path. Then the kinetic energy of this particle is just going to look like 1/2 m times the derivative of S with respect to time squared. Right? Because our speed is really just effectively one-dimensional speed along the track. Okay, so 1/2 m times S dot squared. And since constraint forces do no work, only forces that have a tangential component are going to be forces that do work on our system. So if those forces happen to be conservative, then that means that we're going to have some potential energy function, U, that depends just on S. And so for this situation, we can say that our energy equation looks just like the energy equation for one-dimensional motion. 1/2 m times S dot squared plus potential energy function of S is equal to some constant value of energy. Okay, so this looks exactly like the 1D case, except the motion no longer has to be confined to one spatial dimension. It'll be along some sort of curvy path. It's just parameterized by a single variable. In class on Thursday, we'll go through an example of this sort of curvilinear motion. We'll set up a situation where we have an object, actually a fairly complicated system, that has a two-dimensional motion in general, but it can be parameterized by one parameter. And we're going to want to look at that system and figure out where are the equilibrium points of the motion, and are they stable or unstable equilibrium points. We now have the tools to be able to analyze that, because we know the equilibrium points are going to be wherever this derivative vanishes. All right. How do we determine whether we have stable versus unstable equilibrium points? No, where it vanishes is where we have equilibrium. Yeah, we do the second derivative test, right? If the second derivative is positive, then our function curves upward, and we'll have a stable equilibrium point. If our second derivative is downward, then we have a negative, or we have a local maximum, and so we have an unstable equilibrium point. And if our second derivative is 0, yeah, then we have one of those sort of semi-stable points, right? And we can't tell for sure. There are cases where you actually have a function that looks like this, but its second derivative vanishes. And you have to go to like higher order derivatives to figure out whether it actually curves upward or downward. But we won't worry about those too much. But like x to the 6th would be an example of that. Right? It has an equilibrium point at the origin, but its second derivative vanishes. It's a pretty high derivative function to figure out whether or not it's really stable. All right, so I will see you in class on Thursday. If you have any questions, homework-related questions or anything like that, I'm available now. Actually, my seminar class is in the evening today, and I'll be in my office until probably about 6.
Homework student night.
Yeah.
It's easy. It's not bad. I just don't have any.
It's too easy, you said?
No. I said it's far too hard.
Okay.
Not a dig of, but I don't say something.
I think what he meant is you prepared us so well for this course.
Ooh, okay.
That's
Wow.
He's having a fun time doing work.
That is an
No, I'm having a responsible time
amazing
doing
skewed
work.
reframing.
Yeah. Get my PR representative.
Yeah, I got you.
Anytime I say something,
You need an attorney, or better call Dave.